All right, our next presenter is Katherine Keegan from Emory University. Her field is computational mathematics. Her advisor is Lars Rudotto, and she did her practicum at Lawrence Berkeley National Laboratory.
All right, awesome. Happy birthday, Michael. Hi, everybody. I'm Katie. I go to Emory. I'm glad to see that the World Cup hasn't deterred attendance too much. I used to joke that I would have to put like Subway surfers on the side of my presentations to make people pay attention, but maybe the World Cup would have been a more appropriate choice for today. But yeah, if you'll spare me your 15 minutes, I'd like to talk to you a little bit about teaching science to generative AI. And so I'm a mathematician. I imagine a lot of you are not, and I think that's really important. And I imagine that a lot of you all are domain scientists and experts in your respective fields, and that you've maybe heard about this generative AI for science business. Maybe you work on it already. Maybe you don't really get what all the hype is about. And I think that scientific generative AI is really interesting compared to a lot of commercial applications because we care about two things simultaneously. So the first thing, which we always care about in generative AI, is we care about distributional fidelity. So how well are we modeling the underlying summary statistics in our generated distribution when we compare it to what we would observe in reality? And then the thing that's kind of unique to science is that we also care about constraint adherence. So how scientifically plausible and realistic are our samples from our distributions? And so this is the part that I want to focus on today. The first bullet point, if generative AI researchers will forgive me, is pretty easy. We've put a lot of work into this over the last several years. But in the next 15 minutes, I want to explain and develop some intuition for why the second bullet point is so hard and suggest some ways to inhibit this challenge. And so ultimately, at its kind of bare bones, generative models have emerged as a way to just answer this very straightforward question. How can we model and obtain new samples from, ultimately, an unknown distribution, P0, that's our data distribution, with only access to finite samples from it? So that's our training data. And so this is a pretty flexible question to ask. Examples could include sampling novel protein designs, given ones that we've already discovered, synthetically simulating particle collisions, given previous experiments, or something silly like generating realistic videos of cute animals, given some Instagram reels your friend has sent you. And many leading paradigms can be unified as thinking of P0 as an invertible change of variables from some d-dimensional, super easy to work with distribution, which we're going to call P sub capital T, to our data distribution P0. And so usually we just let P sub capital T be a standard Gaussian because Gaussians. And our only requirement here, or our only kind of implicit assumption in this formulation, is that P0 is differentiable and d-dimensional. And usually, generative modeling amounts to constructing some kind of training and sampling procedure that varies in time, usually continuously, that takes us from T equals capital T, so that tractable, easy to sample from Gaussian, to the data distribution. And all of or most of the continuous time formulations that you know and love, like diffusion models, all fall under this umbrella, as well as some more recent stuff. Now, let's throw a little curveball into our plans. Let's imagine that we have some equality constraint, h of x, on our data distribution. So you don't have to try too hard to imagine this. This is a pretty flexible framework that could include physics and conservation laws, like if x is mass conserved in some way over time, geometrically plausible atom locations, or really any other scientific domain knowledge. And so this is the only time that I'll introduce some crazy math, hopefully. And it's nothing crazy, it's just a level set. And so that's what we're going to call our constraint manifold. It's just the set of all constraint adherence samples, so everything that lets h of x equal 0. So it turns out when we have an equality constraint, we lose all the things that we wanted. So let's imagine that we have a d-dimensional distribution, something simple, and a very, very simple constraint, a line. So this 2D distribution just collapsed to a 1D distribution. And so we've lost this differentiability. We can't differentiate across the line. And we have also lost the two-dimensionality. So our data was two-dimensional, now it's one-dimensional locally because we have a one-dimensional constraint manifold. So the unifying problem here is that we simply cannot find an invertible change of variables between something that's d-dimensional and something that's m-dimensional. That is just a calculus fact. So all continuous time generative models face this pitfall. So You could put your beefiest diffusion model with all of Perlmutter if you really wanted to and try to do this, but you're going to run into this basic fact from calculus. Of course, this has never stopped anybody, but if we do try to train a vanilla diffusion or generative model on such a constrained distribution, we run the risk of a lot of things. So in particular, training and sampling will be kind of messed up because in diffusion models, we have this well-observed phenomenon of exploding scores near the manifold. So that's just the gradient of the log distribution, so just kind of the mechanism we use for sampling. And so we'll end up with a lot of nans and imps during sampling, which renders our samples unusable, basically. And we run into kind of a similar issue with normalizing flows and many other paradigms. And so what we proposed, which was a spotlight at ICML and Seoul last week, which is why I'm so jet-lagged this week, is if the fundamental issue is that there's a dimensionality mismatch between P sub capital T and P naught, we should just resolve that dimensionality issue, and we will lift our data distribution into being d-dimensional using a perturbation. And we're going to construct this perturbation in such a way that if we know that we're going to do projection back down to the constraint manifold at sampling time, we do it in such a way that doesn't distort the distributional fidelity. And so we do this by perturbing only in the directions that are normal to the manifold. So people have had this idea before with isotropic noising. It's been around for like 5, 6, 7 years. But that immediately distorts your distribution when you project back down, even for the simplest constraints, like a line. And for us, for a line, we do not experience those distributional fidelity issues. And so just as a little illustration of what's happening here, let's say our manifold looks something like this. And we have some simple distribution on that manifold, and we have some training data. What we're going to do in our approach is perturb these training data samples only in the directions that are orthogonal to the manifold. And this is going to create a new distribution. That's that P sigma, where sigma is the hyperparameter, the only additional hyperparameter that we introduce, controlling how much we're blurring or how thick this blur is. And so this distribution, this blurred distribution, is what we're going to train your favorite out-of-the-box, off-the-shelf generative model on. So at sampling, we assume that our generative model has modeled this perfectly. That's just an assumption that we make. And so when we sample, what we're going to do is we're going to project back down to the manifold. And the idea is that because of the way that we've constructed this perturbation, the projected error between the projection and the original distribution won't be too bad. And it turns out there's a lot that we can say about this mathematically. So we have linear constraints, which do come up quite a lot in various areas of science. It turns out that P naught and the projected P sigma are exactly the same. So we lose nothing in terms of distributional fidelity and potentially gain a lot in terms of numerical stability. And I really like this because it's you can do a little proof by video. So if I have a line or literally any affine subspace and a distribution on it, and I perturb all of my data points on my distribution or on my manifold, according to our approach, the nearest point on the manifold will always be the original point that you noised from, which is really fun. And of course, nonlinear things are a little bit more tricky, but we can still bound it, which we have in the paper. And now I want to share just a little taste of the experiments that we have. So here we have a bunch of 3D points that lie on a locally 2D manifold, so a sphere, and it forms a nice little smiley face in aggregate. And if we were to use a vanilla normalizing flow, which is just one type of a generative model, or use isotropic noising, we would get these weird projection artifacts after the fact. But for ours, we don't get any of those artifacts. So if we evaluate this on various metrics of distributional fidelity, we see either improved or really competitive performance in sample and distribution quality, which is consistent across sigma. And if we use the magnitude of the log determinants of the Jacobian as a metric for kind of training and sampling stability, we get exactly what we want. So this is the part that we were actually trying to combat, and we see exactly what we want. We also have some kind of brief experiments on very small 10 residue protein backbone generation, where our constraints are bond lengths and bond angles. And we, again, observe what we would want, which is competitive or improved performance on various metrics of distributional fidelity, but more importantly, reduced score magnitude and less diverging of the score towards the manifold, which means we get to keep more of our samples that we spent all of our compute on using. And so lots more in the paper. Shout out Dan Martin for increasing my Perlmutter allocation right before the ICML deadline. And so Perlmutter was instrumental in the making of these experiments and many else that I'll show you in this presentation. But I'd like to talk a little bit about some ongoing work that we have that I think is really fun. So if we know that constraint manifolds cause all of these issues, they cause all this numerical instability as we get closer and closer to sampling time at t equals 0. We've been interested in, does this numerical instability increase at maybe different rates depending on the generative modeling paradigm that we use? So if we kind of know that we're working with a generative, with a constrained distribution, maybe we can choose a normalizing flow instead of a diffusion model, for example, because we know the numerical instability would be less. So that's kind of the question that we've been asking. And so to answer this, we can study the velocity fields that guide individual samples from that tractable distribution over to the data distribution. And so that's what we've been kind of doing in some recent work. And so to get everyone on kind of the same level playing field, I'll remind you or introduce you to some different generative modeling paradigms. So the one that you probably hear a lot about are diffusion models, which are widely considered to be state-of-the-art. Here, samples follow, I don't know if you can see, stochastic paths, and their kind of convergence to a Gaussian is controlled by this parameter called beta of t, which is the noising schedule. Another popular paradigm are flow matching, which follows straighter paths, but they're still slightly curved. So this is nice because you can use a looser time mesh, but it's still not necessarily optimal, which I'll talk about in a moment. One means towards sampling that I really like is optimal transport. And so here, samples follow perfectly straight line paths from our Gaussian to the data distribution. And so this is optimal in the sense that the paths that these samples follow minimize kinetic energy. And so all we have to do is basically one neural function evaluation to do one-step generation. No free lunch, though. Computing OT maps in high dimensions is pretty hard, and there's lots of other things that kind of make this very much kind of ongoing work. But in any case, if we were to look at a very, very simple distribution that lives on a line, so locally 1D embedded in the data dimension 2D, and we were to look at flow matching, for example, under kind of the usual assumptions, then the velocity field induced by flow matching would look something like this as we go backwards in time. So you can't really see anything now, and now we're talking. Okay, so the worst explosion, you can actually derive the constants, but it's in the normal directions at this rate 1 over t. And then if we were to look at diffusion models, remember that there is that additional hyperparameter that is user chosen, so beta of t, that controls how quickly you're converting your distribution into a Gaussian. Then for different choices of beta of t, these are both pretty popular ones. Again, you don't really see anything right now, but things get a little more intense towards t equals 0. And you'll see that the cosine side is kind of diverging more quickly towards the manifold. So you see that the red lines are intensifying on the cosine side more quickly. And so we can still derive that the exact explosion rate for this very simple toy example is happening in the normal directions at rate 1 over beta of t, where beta of t is the noise schedule. But remember, beta of t was something that we chose. So that kind of suggests that maybe beta of t might be a means towards which we can, if you're set on using a diffusion model, control the rate of explosion. And this might be useful for something called early stopping, and I don't mean that in the sense of the training sense, but this is a sampling technique used in a manifold constrained or kind of manifold assumed diffusion models where we stop the reverse sampling process really close to t equals 0, but not quite there. So we do it, or we stop sampling before everything starts going to infinity. So as some conclusions and an outlook on the future, generative models are obviously super powerful and really exciting, but I also don't want you to feel overwhelmed by them. They're ultimately just parameterizations of a change of variables in order to model some data distribution. And the presence of equality constraints, like many of you all probably encounter in science, makes this a really, really interesting math problem. I think this is a really exciting area to work in as a theorist because it bridges these state-of-the-art models that you hear about all the time in the news with what scientists will actually want to use and feel comfortable using. And so I'd love to hear about what you all work on and what kind of probabilistic problems you all are trying to solve. This is joint work with my advisor, Lars, and new friends at Berkeley Lab. This work was brought to you by the following sponsors and viewers like you. Finally, I just want to say thank you so much for an incredible last 4 years. I went to undergrad at a place that didn't even have a computer science department or an engineering department, and so CSGF kind of felt like a shot in the dark. So getting the call from Lindsay really changed the trajectory of my career and my life in a lot of ways. I think something that a lot of people told me at the beginning of the fellowship was, oh, the community is really, really great. And I was like, no kidding. Of course, everyone says that the professional community is great at a lot of these kinds of things. I don't think I realized just how much the personal community would be just as important. So, I mean, PhDs, as many of you already know, have a lot of nonlinear ups and downs. But it's been really, really wonderful to have some lifelong friends that I've met through this program. And I think getting to visit the labs through site visits and getting to hear about all the amazing work that's being done at the national labs over the last few years at the program review has really renewed my sense of optimism in American science, which is hard to do in the last several tumultuous years. So I can't thank Lindsay and Michelle and everybody in the program enough. And on that note, I am happy to take any questions.